Welcome to the session on statistical distributions, probability distributions. The objectives for this session are to understand and use simple discrete probability distributions, such as the discrete uniform distribution. Let's begin by looking at some notation and definitions related to statistical distributions, and also some examples which relate to all of these. We begin with a random variable. A random variable is a variable whose value depends upon the outcome of a random event. A sample space is a range of values which can be taken by a random variable. A variable can take a range of values. A discrete variable can only take certain numerical values. A random variable is denoted by uppercase letters, for example, capital X or capital Y. Particular values which a random variable can take are denoted by lowercase letters, for example, little x or little y. The probability that a random variable x takes a particular value x is written as probability of capital X equals little x. And finally, a random variable is an outcome which is unknown until after the experiment. So that's quite a few definitions. We're going to tie all these definitions together with one more definition and then explain all these definitions with an example. A probability distribution fully describes the probability of any outcome in a sample space. So now let's start to look at an example, which will hopefully help us to understand all this notation and all these definitions. Our example is a random variable is capital X equals the score when a fair die is rolled. The probability mass function, probability of x equals 1/6 for x equals 1, 2, 3, 4, 5 or 6. Let's present this in the form of a table. We have little x and the values it can take in the top row and the probabilities of each of these little x's occurring in the second row. In terms of a diagram, the probability mass distribution or probability mass function will look something like the one you can see on your screen now. And remember that a discrete uniform distribution is when all the probabilities are the same. So in this example, we do indeed have a discrete uniform distribution because all the probabilities are 1 out of 6. Now let's see how the example relates to the notation and the definitions. So in this example, the random variable is the variable whose value depends upon the outcome of a random event. Our random variable is capital X, which is the score when a fair die is rolled. Notice that our random variable has been denoted by a capital X, and of course its outcome will be unknown until after the experiment, and in this case until after the die has been rolled. And now for the sample space. Notice here we have the full range of values that can be taken by our random variable, so 1 all the way up to 6. Also, notice, of course, the variable can take a range of values, as we just mentioned, and the particular values which the random variable can take has been denoted by the lowercase letter x. And in this case also, we have a discrete variable, so it can only take a certain number of numerical values. And these are exactly 6 values which it can take. And of course, we also have the probability of x equals little x. And the sum, notice, of all these probabilities is equal to 1. And again, as we mentioned earlier, because all the probabilities are the same, we have a discrete uniform distribution. Now let's take a look at another example. We're going to let our random variable x be the number of heads when 4 fair coins are tossed. The possible outcomes are given here in the middle of your screen. So we have heads, 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 tails, heads, and so on. We can present this in a table. So, little x can take the value 0 heads, 1 head, 2 heads, 3 heads, or 4 heads. The probability of 0 heads, let's consider this. There's only one outcome where we have 0 heads, and that's where we have 4 tails. So the probability of 0 heads is 1 out of 16, which is the total number of outcomes we could have. The probability of getting 1 head is 4 out of 16, because we have 4 ways of getting exactly 1 head, as highlighted on your screen now. So the probability that x equals 1 is 4 out of 16, which is of course equal to 1 out of 4. What about 2 heads? What's the probability x equals 2? There are 6 ways of getting exactly 2 heads, as highlighted. So the probability of x equals 2 is 6 out of 16, which is of course equal to 3 out of 8. And what is the probability that x equals 3 heads? That is of course equal to 4. So there are 4 ways, as highlighted, of getting 3 heads. So the probability of x equals 3 is 4 out of 16, which is of course equal to 1 out of 4. And finally, what is the probability of getting 4 heads? Of course, there's only one way, and that's heads, 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 heads. So the probability of x equals 4 is 1 out of 16. We can check that these are correct by adding up all the probabilities and seeing that they equal 1, and they do indeed equal 1. And now let's have a look at the probability distribution function. This is going to look like this. So probability that x equals 0 or 4 is 1 out of 16. Probability that x equals 1 or probability that x equals 3 is 1 out of 4. And probability that x equals 2 is 3 out of 8. So let's now take a look at how our example relates to the definitions and the notation. So of course our random variable is x equals the number of heads when 4 fair coins are tossed. So of course our random variable has been denoted by a capital letter, which is x, and the particular values which the random variable can take will of course be denoted by little x, which has also been highlighted. The probability distribution function puts the capital X and the little x together as shown here. Of course, another key point is that all the probabilities added up together give us 1, as shown. And out of interest, we can calculate various probabilities from this table. So for example, if we wanted to know what is the probability that x is greater than or equal to 2, we ignore probability x equals 0 and we ignore probability that x equals 1 and only add up the probabilities that you can see highlighted on your screen. So probability x equals 2 plus probability x equals 3 plus probability x equals 4. And similarly we can calculate other probabilities as well. So the probability that x is greater than or equal to 2 is equal to 11 out of 16. This brings us to the end of this session. If you have understood its contents, you should be able to understand and use simple discrete probability distributions, such as the discrete uniform distribution. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.